Good day everyone. In this video, let us discuss the crash course on the electric potential. Now, we learned in our previous video that when two interacting objects or more, it generates electric force, or we call that as electrostatic force. And the magnitude of that can be calculated using the Coulomb's law, where it requires the magnitude of the two charges and its distance between center to center. So it provides a force, and that maybe will cause motion to the charges. Another thing is we learn also that for all charges placed on a certain point, it generates electric field. And that electric field is proportional to the magnitude of the charge, source charge, and inversely proportional to the distance from the source charge, which means that if R is reaches approximately towards the infinite, then the electric field is approximately equal to 0. But if the point of interest is approaches closer to the source charge, then the electric field becomes greater and greater, and it is maximum at the surface of the charge, and it is 0 if it is inside the source charge. Okay. Now, today, let us have another physical quantity in electrostatics that are very important, because this is where that we can understand, or we can provide answer why voltage is being produced. So first we will discuss the electric energy, and we assign that as big letter U in our mechanics, and consistently we use also that symbol, electric potential energy. And we have the electric potential, and we assign that a big letter V. So take note that electric potential is different from electric potential energy, because the energy has a unit of joules, but the electric potential has a unit of volts. So they are different to each other. But this electric potential is directly proportional to the potential energy, vice versa. And the unit of electric potential is volts. So they are different to each other. And after that, we will come up with the questions why voltage is being produced, and that's by studying the electric or the potential difference. And that will be the potential difference between 2 points, and we call that as potential difference from A to B. Okay, so these are the topics that we will tackle in this video. And this belongs to lessons 1.4 in the learning module. Okay, so let's start with the electric potential energy of a single charged particle. Okay, so if we consider a charge, positive charge placed on a certain space, and whose magnitude is Q, and having a unit of Coulomb. Now take note that this will generate an outward distribution of charges, and we call this as electric field, or the intensity of electric force with respect to a certain point charge. Okay. Now, if we place this in a Cartesian so that we can locate other particle, so let us say I have here the discharge whose magnitude is Q naught, and this is positive. So this is located in the first quadrant. Having a position vector of RA means the location is located at a distance or a vector position RA. Now, take note that this force, or this charge, experience a force due to the source charge Q. Now remember that magnitude of Q is greater than compared to the discharge, and this is actually a moving charge, while Q, we call that as stationary or source charge. So the moving charge is subjected by an electric force, and this force is tending to move away, because positive in the law of electric charges repel. So which means that this discharge or Q naught will move away from the source charge. Okay? So then, it will move at a certain distance. Let us say the position is RB. This is the final position of the charge Q naught. Okay, since particle travels, then there must be a force. And because we have a displacement, then it provides the so-called work done by the charge. Now remember that generally, when we say work done from A to B, from one point to another point, or from initial to final point, work done can be calculated using the dot product of the force and its displacement. So, in general mathematical presentation for work done, we use the integral, no? The integral of the dot product of force dot infinitesimal displacement. So, infinitesimal displacement, it is a very, very small change in position. Take note, we have two positions, RA and RB. So the RA will serve as our initial limit or lower limit, and the RB will be the upper limit. So if we evaluated this integral, the result should be the work done by the charge from A to B. Okay? Now take note that the dot product in mathematical or the vector analysis, that product is just the magnitude of two vectors multiplied by the cosine function of the angle between the two vectors, the force and the displacement. So we can evaluate this dot product by having a magnitude of the force and its displacement, and we have the cosine of the angle theta. Take note, the angle theta is the angle between the two vectors. Now, since the force is tend to move away from the source charge and it displaces also in that line, then it follows that the angle between the force and the displacement should be 0. So if we substitute the value of 0 for the angle, the cosine of 0, remember, is 1. So it will reduce to the integral from RA to RB of the force times the infinitesimal displacement. Again, dr means the infinitesimal displacement. It is a very, very small change in position from A to B. And remember, this force is at any point of travel from A to B, which means that this force will vary depending on the position of R. And R is the position at any point of the travel also. So then we will have to replace this force. Remember, in Coulomb's law, we learned that magnitude of force can be calculated by 1/4 pi permittivity times the product of the two interacting charges divided by the square of their distance, center to center. The distance is R. Okay? And the two interacting charges are Q and Q naught. And the 1/4 pi permittivity, we call that as electric constant. So we can replace it, and having this one as the 1/4 pi permittivity Q naught over R squared. Again, R is at any point of travel from A to B. And this increases, take note, as the particle travels. So when you look at this integrand, there are constant, no? Meaning, when we say constant, it will not affect, no, if we evaluate the integral, it will not affect to the variable. So the constants are 1/4 pi permittivity, Q and Q naught. So therefore, remember in calculus, constant cannot be affected by differentiation and integration. So we can move it out so that we have this value. So this will be a simplified form. Okay. So we have Q over Q naught over 4 pi permittivity, the integral from RA to RB, of what? 1/R squared dr. So take note that the integral or the independent variable is R. So we have this R will vary, no? So we are now about to evaluate this integral. So evaluating the integral is we have to use the theorems of integration. So in this case, we can apply the power rule of integration. Power rule because if we move this R upward, this will be, or above, no? In the numerator, we have to change in the log sign, we have to change the exponent into a negative value, from positive to negative or negative to positive. So this will becomes r raised to negative 2, and negative 2 is the n value of the power rule. So it reminds us to recall our calculus. So therefore, applying the power rule is n as the power of the function added by 1, then it should be divided with the same n plus 1. So if we add 1 to the negative 2, this will becomes negative 1. So meaning we have to divide both sides by negative 1. So it will result a negative answer. And that is 1 over r only. Okay, because it was subtracted by 1. So the evaluated value for this expression, okay, the integral of 1 over r squared is dr. And the answer is 1 over r. Then it ranges from lower limit RA to RB. Take note negative because this is the result after evaluating the integral. Okay? Now let's apply the limit. Limit means upper minus lower. So we have this one. Substitute R with RB in the upper. Then next for the lower, which is RA. Okay? So we have this as the result, no? If we are about to calculate the work done. Take note that we are about to calculate how much work is done on the charge Q naught traveling from RA to RB. Okay? Now look at this term. If we distribute this 1 over 4 pi permittivity inside the grouping symbol and we leave this negative sign outside from the grouping symbol, so distribute by multiplication, then we have this result. Now we have negative quantity Q naught over 4 pi permittivity RB minus Q naught over 4 pi permittivity RA, close parenthesis. So nothing will change, and this is according to the law of algebra. But take note that when you look at the terms inside the grouping symbol, we have similar, no? Almost similar expressions, but they are not equal. Why? Because it varies with R. This is RB and this is RA. So the only difference of these two terms is only the RA and RB. Okay? Now, this one is the definition of, we call this as the definition of the electric potential energy. So this is called as the electric potential energy final. Final because RA is the position final, which means that the second term is also an electric potential energy, and that is initial. Okay, so we assign UB means electric potential energy in the final position, and UA is electric potential energy in the initial position, which means that inside this one is just the energy of the charges from initial towards the final, and this is final minus initial. So meaning, if you are asked how much is the energy initial, then we have to use this, and this will serve as a formula. And the answer is 1 over 4 pi permittivity. Take note that 1 over 4 pi permittivity is electric constant, so nothing to worry. The value is 9 times 10 raised to 9 Newton meter square per coulomb square. So we have this one as a constant. Then we have to multiply the two charges, the source charge and the moving charge, Q naught, over RA. So this is the answer if we evaluate this using this formula. So meaning we can calculate the energy at point A, and the unit is in joules. Okay? So then we have, again, if you're asked of how much is the energy in the final position, then the answer is 1 over 4 pi permittivity Q naught over RB. So as long as you have the two charges, interacting charges, and you are about to find the energy, then you should have the distance. So it requires three parameters: the source charge, the moving charge, and its distance away from the source charge. Okay? So, meaning, this is the general definition of what? Of electric potential energy of a single charge. Remember, single charge particle, meaning one charge and the other charge that interacts is only one charge. Take note, the unit of energy is joule. This is consistent with our understanding in mechanics, that energy work and also the work and energy, the unit is in joule. So therefore, since the unit is in joule, then it follows that again because take note that we use the dot product for the work done, then meaning to say that work done is a scalar quantity. So if the work done is scalar quantity, then electric potential energy is also a scalar quantity. When you say scalar, magnitude only. Nothing to worry with the direction because it cannot describe. No? It describes only by its magnitude. Okay? Now, we have another unit of energy, the electron volt in electrostatics. No? When we say 1 electron volt, it is equivalent to 1.602 times 10 raised to negative 19 joules, which means that the 1 electron volt, it requires 1 electron and 1 volt of potential. So meaning we can provide a unit of joules here. Meaning if the given is in electron volt, we can convert that into joules because joule is the unit of energy for SI. Okay, or for SI unit. And take note, this is scalar quantity. So when we say scalar, again magnitude only, then it must have a positive energy or maybe a negative energy. So how can we say that it is a positive? Then look at the formula. If the two interacting charges are positive or same sign, then the energy should be positive, meaning positive, positive, energy is positive. If this is negative source charge and negative test charge, then the energy is positive. But if the two charges are different in magnitude, meaning positive, negative, or negative, positive, then that's the time that the energy is negative. So when we say negative, the two charges are different to each other in magnitude. If it's positive, means to say that they have the same sign. Now, what about zero? Okay? Remember that it can be positive, negative, or zero. So how in what case that the energy becomes zero? Now take note that source charge and moving charge cannot be zero. The R cannot be zero also. Okay? Cannot be zero because the minimum R should be at the surface of the charged particle only. So from its center towards the surface. So the minimum R is the radius of the charged particle. So it is maximum at that point. Why? Because this is inversely proportional. The smaller, the greater. So if you want to zero the energy, the zero can be located in a far away distance. Meaning, if your R approaches infinite, then that's the time that energy becomes zero. Okay? So if we substitute this one, because we learned that this is initial or the final electric potential energy, so assign this as UB, while this one is initial electric potential energy. Then, meaning inside the parenthesis is just the UB minus UA, or the change in electric potential energy, which means that work done by the charge traveling from A to B is just the negative change in electric potential energy. So this formula is very familiar in our mechanics, and it is true, no? That all potentials, the change in potential, the change in any potential, the negative change of any potential is the work done by the moving charge. Okay? For example, work done by gravity. The work done by gravity is just the change in gravitational potential energy, negative change in gravitational potential energy, which means it reduces its energy. No? From, for example, the gravity from the higher level, if we release the object towards the surface, the energy, the potential energy, is keep on decreasing. Okay, keep on decreasing. That's why it has a negative change. Also with elastic. it is also a negative change. So therefore, consistently, we provided the proof that the work done from A to B is equal to the negative change in electric potential energy. Okay? So, again, this is only applicable, the 1 over 4 pi permittivity is applicable only for single charge particle, meaning there is only one charge that surrounds to a certain charge Q naught, or vice versa. Okay, now take note again, this energy can be zero in the far away distance. So if we substitute R to an infinite number, then it's approximately equal to zero. It is not equal to zero. It is approximately equal to zero. So, but if R decreases, then this energy increases its magnitude. And the maximum again is at the surface. Inside is constant, no? Meaning constant. Constant, the electric potential is constant, meaning at from the radius, no? Less than the number of radius, it has a potential the same as in the surface. So we can say that R is equal to zero. Okay, so again, if you are asked to calculate what is the work done of the charge, then use the negative change in potential energy. Now, if you notice in our mechanics, the gravitational force is what? Our gravitational potential energy is the product of mass times the gravity times the height. Okay? But this one, for the electric potential energy, it is 1 over 4 pi permittivity Q naught over R. Okay, so let's have this example. Suppose I have 30 microcoulomb placed at the center of at the origin of the Cartesian. So this is a positively charged. And I have here a moving charge, let us say 10 microcoulomb, at a distance or having a mass of 3 kilograms. And it has a distance from the source charge of 2 centimeter. Okay? Now, if it starts from rest, because this particle will travel, if we release this one, if we release this initially, we release that freely, then the initial velocity should be zero, and it increases until it travels a certain distance, let us say 5 centimeter. The question is, calculate the final velocity, meaning solve for V sub 2. Now, how will you answer this one? Okay? So, to answer this is, we have to recall in our mechanics the conservation of energy. Now, remember that energy is always conserved because we cannot destroy that energy. No? We cannot create that energy. The only way is to transform the energy. So we can transform the energy from one point to another point, but energy is always constant. It will never change. So energy is always the same, which means that if we apply conservation of energy from point 1 to point 2, then energy should be the same. Meaning the total energy initial should be equal to the total energy final. Now, take note that in this case, there are two energies, the kinetic energy and the potential energy. So in mechanics also, we have two energies, the kinetic energy and the potential energy. But sometimes there are external forces, so we have added by work done by the other. But in this case, we assume, take note that we did not consider the gravitational effect. We consider only the effect of charges. So we can imagine that we place this in a vacuum, evacuated area. Means there's no other particle that interact except the charge, the two charges. Okay, so we can ignore the mass or the effect of gravity. So therefore, there are only two forms of energy, the kinetic energy and the electric potential energy. So the initial energy is just the sum of the kinetic energy 1 plus potential energy 1. While in the final energy total, it is the sum of the final kinetic energy plus the electric potential energy final. Okay? Now, how to answer this? How to substitute the kinetic energy and potential? So we have to use the formula that we derived previously. Okay? So take note that the formula for the electric potential energy due to a single charge particle, U is 1 over 4 pi permittivity Q naught over R. So in this case, nothing to worry because we are given with the source charge as positive 30 microcoulomb and the moving charge is 10 microcoulomb. And the distance, no? Take note that we have this distance 2 in the initial and 5 in the final. So nothing to worry as far as the potential energy is concerned because we have this formula and we have this data. Now, kinetic energy, take note that it is the same as the kinetic energy in aeromechanics. It is 1/2 mv squared because kinetic energy actually a function of its velocity. So when there's velocity, there's always kinetic energy. But if the velocity is 0, then the kinetic energy is 0. So when you look at the initial point, this K1 or initial kinetic energy is actually 0. Why? Because the velocity is 0. It is at rest initially. So nothing to worry with the first term in the left member. But the second term in the left member, the U1, we can substitute it with the formula. 1 over 4 pi permittivity, Q, which is 30, Q naught is 10, and R is 2. Okay, so do it that way. So this is it. This is our U1. And this must be equated by K2 and U2. But K2 is, what's K2? If K1 is 0, K2 is not 0 because we have here the velocity. And we don't know this velocity. So since we don't know the velocity, but we have this mass, so we can use the formula by 1 over 1/2 multiplied by the 3, which is the mass, times we don't know the velocity, then square it. And the final potential energy is again the formula 1 over 4 pi permittivity Q naught over R, then do it that way. So we have 1 over 4 pi permittivity plus 30 microcoulomb, or the positive. Take note that we emphasize here the sign of the charges because take note that the energy can be positive or negative. So consider always the sign of the charges. So positive, positive. So the result is positive. Then we have over 5 because this is the final position. Take note that the final position or position is always coming from what? The source charge. No? So meaning if the given is displacement, the displacement is 3, then you have to add that by 2 for the R position final. Okay? Now look at this equation, result equation. We have only one unknown. No? So meaning we can solve for V2. But take note that the units are inconsistent. Inconsistent because the microcoulomb is not an SI. Centimeter is not an SI. And take note that we will be using, for the 1 over 4 pi permittivity as the electric constant, we will be using 9 times 10 raised to 9. And the unit is Newton meter squared per coulomb squared. Which means that we need to convert this micro to coulomb and centimeter to meter. Now remember that in our previous, we learned that the 1 microcoulomb is equivalent to 10 raised to negative 6. So meaning, if I convert this 30 microcoulomb to coulomb, I just multiply it by 10 times 10 raised to negative 6. Also true with 10 and the opposite side. No, we have 30 and also 10. So we have each of these will be multiplied by 10 raised to negative 6. Now, for the centimeter, remember that 1 centimeter is equivalent to 10 raised to negative 2 meter. So in order to convert the 2 centimeters, just multiply this by 10 raised to negative 2. That's it. And the answer now is meter. So doing that is we are creating the consistent unit of this equation in order to manipulate this and solve for the final velocity. So this is the result. So we multiplied it by times 10 raised to 6 for the micro and 10 raised to negative 2 for the centimeters. So 5 and we have 2. So again, we are now ready to use our calculator. So simplify this term, this one, and this one. So we have 3 terms. So the first term is 35, sorry. And this one is 1.5 b square, b sub 2 square. And this expression is 54. So you can double check the calculations. Now in algebra, you have to transpose this, then divide both sides by 1.5, then take square root, and the answer is 7.35 meter per second. This is the velocity of the particle in the final position. So if it starts from rest at a distance 2 from the source charge, then when you release it, it travels 5 centimeter, then the velocity is 7.35. Okay? Then it will keep on increasing until it reaches the maximum velocity that it won't stop anymore. And it will provide a constant velocity, a certain point. But take note that when you release, it is keep on increasing its magnitude until again reaches the terminal velocity. So for now, the velocity is 7.35 meter per seconds. Okay, so this answer to the problem. Now what will happen, because our energy is actually, formula is for single charge particle, what will happen if there are 2 or more? And in this case, we have 3, no? We have the positive Q1, negative Q2, and negative Q3. It can be positive or negative depending on the given. So what will happen, by the way, we call this as a multiple charge particle. So we use the term multiple for energy. If you notice, in our force and electric field, and if there are 2 or more, we call that as superposition. No? We use the superposition because we say that at a certain point, there are superpositions of the vectors at that point. So we need to use the vector sum. But in this case, because this is scalar, we can use the multiple charge particle, meaning it doesn't matter the direction on this. So what will happen if you are asked to calculate the electric potential energy for this multiple charge particle? So let us say at that point, what will you do? First thing to do is you need the R. No? From each charge should have a distance towards the point of interest. And the point of interest is the location of Q naught. So we need the magnitudes and we need the positions from each charge going to the location of the discharge. So in that case, what is the energy due to the multiple charge? Nothing to worry. All you need to do is to add its energy, for each particle that surrounds. You have to add it algebraically. So when we say algebraically, add always, but there are cases it will become negative depending on the charge. Okay, the result of the two. So take note that the formula is 1 over 4 pi permittivity, Q naught over R. Now in this case, the first, meaning we can apply in a multiple charge particle, we can use the formula for a single charge. So do it individually, each charge. So the number of charges that surrounds are the number of terms that will be added. So first we have 1 over 4 pi permittivity, charge 1, Q naught over R1. Then in the second term, 1 over 4 pi permittivity again, negative charge, because in this case our example is negative charge, it can be positive depending on the value, multiplied by the discharge, then over R2, and so on. Okay, if there are 4, then go. Okay, so this is it. No? Then add it algebraically, and the answer is the electric potential energy for a multiple charge, and this is due to the surrounding charges also. Now take note that we have common here, 1 over 4 pi permittivity Q naught. So we can simplify this, to make it simple. So you can use this Q naught over 4 pi permittivity, or like electric constant multiplied by the source charge, then, the discharge, then you have to divide the charge source charge 1 by its distance from the uh, test charge, then do it similarly but algebraically. So negative Q naught, Q sub 2 over R2 and so on. Then that's it. No? So again, this is the electric potential energy due to multiple charged particle. Now we can present this in terms of power series in order to make it convenient, no, for us to handle, and we avoid this dot dot dot. So we can use this power series. So this Q naught over 4 pi permittivity is this one, while in this parenthesis, and we sum up. Take note. So we use the word sigma for the power series, summing up all. Now we have to sum up all. I start from 1 to any number. Let us say 10. For example, there are 10 charges. So this will be 10. And take note, for 10 charges, 10 terms also should be added. Now the Qi over Ri corresponds to the individual charges. So I starts from 1. So meaning, first, it starts from 1. This will become Q1 over R1 plus, if this will becomes 2, then this will be Q2 over R2, and so on until Qn over Rn. That's it, no? So this is a nice presentation, mathematical presentation for this kind of summing up numbers. We call it as power series. Okay, so that's it. So again, if we have the source charge and we have the moving charge and we have the radius, we can always calculate the energy. U is 1 over 4 pi permittivity Q naught over R. Now, if I divide, look at this one, if I divide the energy at that point and divided by the moving charge and its charge Q naught on that, no, value, meaning U over the discharge, then the answer is electric potential. This is electric potential. Remember, U is electric potential energy, V is electric potential, which means that the electric potential is actually the energy per charge. Energy per charge. If you have more charge, then you have more energy. Okay? So, meaning, be careful that because we want to know how much is the potential at this point where located, no, the location of the discharge, then you have to divide respectively its energy and its charge. Now, if you do this one, the energy at this point in the source charge divided by the source charge, then you are looking for the potential, electric potential at that point respectively. So be careful in dividing the two interacting charges. So since we use U, Q naught, then it should be the potential at that point and its energy also. Okay, so this is the electric potential due to a single charge particle. Now, meaning, take note that this is energy per charge, diba? So this is the definition of electric potential. So the unit should be volts. Why volts? Because this is joules per coulomb. Now remember that joules per coulomb or 1 joules per coulomb is equal to 1 volt. And the volt unit is SI. Joules per coulomb is not SI. So we use the unit of volt. But take note that when we do the conversion or verifying the units, we need to replace the volt by joules per coulomb in order to see, no, the real unit of that quantity. But in SI, we use volt. So 1 joules per coulomb is 1 volt. That's why if we have one potential, 1 volt, multiplied by electron, 1 electron, we call that as electron volt. And 1 electron volt is 1.602 times 10 raised to negative 19. Okay? So, that's it, no? We have this conversion factor or equivalent of the volt. Okay, so remember that we can solve the potential if we have the energy per its moving charge. Now, what if we don't have the energy? Now, if we don't have the energy, and we have the source charge and it's moving charge, then you can use the definition of the energy by using 1 over 4 pi permittivity Q naught over R. Now look at the result. Take note that we can remove, di ba? We can cancel Q naught because they are equal mathematically. So if we cancel Q naught, it will reduce to 1 over 4 pi permittivity Q naught. So actually, we are removing the Q naught in the energy. If we remove the Q naught, the answer is electric potential. But if we multiply that potential by the moving charge, the answer is energy. Okay? So, very clear. So, take note, this is what? Electric potential energy due to single charge particle. And the unit is volt. Okay? Now, this is also scalar because work is scalar, electric potential, energy is scalar, electric potential should be scalar also. Meaning, it has zero, it has negative, it has positive value. So, the potential is positive if the charge is positive. Okay? Now, if the charge is negative, then the potential is negative also. The potential is zero, what? Why? In what point? In the location of our approaches negative or approaches infinite distance. That's it, no? So if you are asked what is the potential at this point, then simply use this formula. Again, 1 over 4 pi permittivity Q over R. That's it. Very easy to handle. Okay, so what will happen if we have multiple charge particle? Now, if we have multiple charge particle, and you are asked how much is the potential at the point where Q naught located. So, say in similar way, we need what? The magnitudes of the charge itself, and its distance towards the point of interest. So we should have this distance. With that, we can now calculate the question, what is electric potential? This is the same as we did in our previous slide. We calculate U, no? But it differs with the formula. So how can we solve? You can use the single charge particle formula. On each charge, then you have to add algebraically, similar way. So we have this 1 over 4 pi permittivity, Q1 over R1. Notice that in energy, we have Q naught here. But in this case, we don't have Q naught. Okay, so then plus negative, because this is negative charge, we have R2. So similar way. Okay, then we have common here. The common is 1 over 4 pi permittivity. Then this will reduce to this one. And again, this is the electric potential due to multiple charge particle. So nothing to worry. Okay. Now in power series again, we use the 1 over 4 pi permittivity. I is equal to 1, and this is up to n power, and we have this, or up to n terms, then we have Qi over Ri. So the same, we can use any of these two, but this is the exact presentation of the power series form. This is a power series. Okay, so let us have example. Suppose we have two charges, no, placed on evacuated empty space, no. One is 30, the other is negative 30 microcoulomb. So actually, we call this the electric dipole. Similar charge. Yeah, we have the different sign. Then they are spaced in, let us say, 4 meters away. So the question is, how much is the electric potential at that point? So what will you do? You need to have this distance. So know this distance. Then know the distance from the other charge. So we need this distance from each charge towards our point of interest, because you are asked how much is the electric potential at that point. So how to answer? Again, use the multiple charge particle principle on the electric potential. So we have to add the potential due to this charge. So it should be 1 over 4 pi permittivity, but by the way, I use the plus sign for the positive to recognize. But remember that we need to multiply this. Okay? So 30 plus 10 raised to negative 2. negative 6 for the micro. Then divide by 2 because this is 2. Then, in the second, because we have two charges, the number of charges surrounds are the number of terms that we need to combine algebraically. So again, we emphasize the negative here. So this is negative value and divide by 4.5 because it's the distance, and this should be multiplied by the electric constant. Beware sa pag-subtract. It is a negative multiplied by a positive. So practically, this is what negative and this is positive. When you look at the two, this is 4.5 and this is 2. So meaning, this term is less than compared to this one. So the result should be positive. Okay? So the answer is positive 75,000 volts. So what's the meaning of that? Why is it positive? Yeah. Because this point is closer to the positive charge. So if it's closer, this term is greater compared to this term. Okay? So practically, if you find, if you have the location and that's closer to the positive, it might be a positive potential. Remember, we have the positive potential and we have negative potential. Now, what will happen if the point of interest is close to negative? So, meaning this is approximately, or this is obviously a negative term. Okay? When you look at the mathematical solution, diba? So, by the way, we need the distance. Suppose this is 5 and this is 3. Okay? And this is 3. And this is closer to negative. So when you substitute the values to find the potential, this is 5 and this is positive charge added by negative charge over 3. This is 3. So this time, this is greater compared to this value. Why? Because the smaller the denominator, the greater the number. So when you evaluate this one, obviously this is negative answer. This is negative 36,000. So at that point, 3 meters away from negative 3, and this is 5 meters away from positive charge 30, then the answer is negative 36 volts. So therefore, in analysis, if you want to have a negative potential, place the point near the negative charge. Okay? And if you want to have a positive potential, place that closer to what? Closer to positive charge. Look at the two values. Okay? Look at the two values. This is in magnitude 75,000, while this one is only 36. Why? Because this is 2 and this is 3. And this is closer compared. Remember, they have the same magnitude, okay? So, meaning if I reduce this to 1 meter, this will increase. But if I move this away, this will be decrease. Okay? So meaning, if you want to know where is the location of a greatest potential of the two interacting charges, or we have the multiple charges, then place that at the surface of the charge to obtain greater potential. And this one, if you want to obtain a greater negative potential, then place it at the surface of the negative charge. That's it, no? Now, what will happen if I have this point? You want to locate or you want to know how much is the potential at this point due to the multiple charge particle in a dipole at the midpoint. So, meaning, suppose this is 2.8 and this is 2.8, how much is the electric potential? If this is positive and it's negative, what do you think was the answer? Remember equidistance, the same distance. So when you substitute this distance, this is 2.8, okay, this is 30, added by the same charge but negative, take note the same value. So meaning, this term is the same as this term. For equidistance, the potential is 0. Meaning, if you are asked how much is the electric potential at the midpoint of the electric dipole, then the electric potential is 0 at equidistance. So, meaning if you connect this line upward, then for all equidistance from the source charge, the electric potentials are equal to 0. So, meaning you can imagine a line here having what? Having potential equal to 0. Now, at that line, if you move a little bit towards right, it will becomes negative. At that line, again, move a little bit to the left, it will becomes positive. So, we call this as the boundary limit between the positive and negative. The 0 is the boundary between positive and negative potential. That's it, no? Okay? So, meaning, if you rotate around this region, you can always find the electric potential. Now, if you want to have this simulation of this, you can visit the FIT, no? FIT simulations. You can search in the Google PHET, no? for simulations. There are a lot of simulations there, and one of that is for the charge, no, or the electric potential and electric field, no, simulation. So you can visit that website. It's a very nice simulation. Okay, so look at this one. So I have potential A, I have potential B. So what if I want to subtract the potential A and potential B? So if you subtract A and B, we call that as potential difference. This is potential difference. Okay? So this is the last quantities that we need to calculate, the electric potential. And this is very important. Why? The electric potential difference, we call this as voltage or electromotive force. If you want to run or if you want to work to operate your appliance, we need voltage. Take note of that. And the voltage is a power supply, source of energy. So where is voltage coming from? The voltage is coming from the potential difference. What is the potential difference? It is the energy per charge at a certain point. Okay? So, if I subtract, because I have here potential voltage, 75,000, and this is negative 35,000 volts. If I subtract A and B, we call this as the potential difference from A to B. If you reverse B minus A, it is a potential difference from B to A. Take note, this is not change. It is potential difference. But change is different to a difference in potential. Okay, so that's it. We have this as the potential difference or the voltage. So if you do the manipulations, so substitute this VA here, and this is VB. Take note minus because difference always minus, but this is minus. So therefore, the potential difference is 111,000 volts, or the voltage of this point at these 2 points. We need 2 points. In order to obtain voltage, we need 2 points. We call it as terminal, no? Terminals of the source. So we can utilize this as a source for the 2 points. So the answer is 111,000 volts. So we add the two. Meaning, if you want to have a greater voltage, make sure that one is positive, the other is negative. Why? Because if both of them are positive, when you subtract it, the number becomes lesser value. You have to subtract its value. Now in this case, because they have different polarity, then when you subtract it, it will accumulate. The magnitude will be add up. In short, in order to produce, because we need to higher voltage in order to operate appliance, no? So if there's a chance to have it, then go with that. So therefore, find a point here that provides greater voltage. So, but take note, this 111,000 can be increased, di ba? If we move this one and place that at the surface of the charge, this is much greater than 75,000. And if we place this at the surface of the negative source charge or negative charge, then this is much greater than. In fact, it is a maximum at the surface. That's why place it at the surface of the positive, and this one be to the negative surface. then it provides the greatest voltage. Okay? So we call this as the potential difference or voltage, or sometimes we call this electromotive force. That's it. These are the terms. And this is very important because we are working with appliance, no? In order to operate the appliances, we need to have the voltage. Our power source here in Liti, from LICO, no, from the single power, the voltage is 220 volts. And take note that it is alternate current, means the polarity is not fixed. Sometimes positive, sometimes negative. So if one is positive, the other is negative, vice versa. So we call that as a standby power supply. So anything that we use it, you can have it. You can plug in and it serves energy. And remember, the voltage is electrostatics. The energy at rest, the potential energy, di ba? It is at rest. But if we use it, then it will work on the appliances. Okay? So that's why if we have the battery, if you notice, there are two terminals of the battery. One terminal has a red color, sometimes, the other is blue or sometimes black. So one of that has a potential. Say it potential A, electric potential, and the unit is volts. Remember. Now other terminal, we use we can say it VB. So we have two terminals. Now take note that in order to, di ba, we use the battery to supply energy. So we clamp it to ensure that we connect it at the surface. Remember, positive charge and negative charge is present on the terminal. That's why we have the greatest potential at that point. So meaning, if I subtract the two, the result is voltage. Therefore, in order to have standby power, we need to connect the 2 points, the positive and negative. Because you cannot provide a voltage if you have only one terminal. There's no voltage happen if you connect only one terminal. Because there's no difference. Voltage requires potential difference, meaning it should have two. One is positive, the other is negative. Why? Because positive negative, because it will provide the greatest voltage. So meaning with that, we can say that the battery has a potential difference from A to B if we substitute the values present on the terminal. So remember, in battery, suppose this is 6 volts positive and the other is negative 6 volts, then what is the potential difference? So subtract it, but positive, the result becomes 12 volts. Okay? So this battery is at 12 volts, sometimes 24 volts. Remember, the battery is a portable source of energy. So if you remember sa atong voltage cell, we have two electrodes. Okay? Two electrodes, the dissimilar plates, no? Diba? Positive, one is negative. Then it plays on the electrolytes. So electrolytes can be liquid form or dry form. So kung liquid, we call it as wet cell battery. If it is powderized, we call it as dry cell. So dry cell battery, it has electrolyte of powderized material. But wet cell or car batteries uses the liquid form, usually acid. Okay? So, but conventionally, we use, if one terminal is 12 volts, the other terminal is 0 volts. 0 volts means we use it as a ground. But remember, without the ground, you cannot provide the voltage again. So normally, when we see negative, we call it as ground. So in our household, the source from the source, no? Source from our national power. One is active, the other is ground. So the higher voltage is on the active, no? Or live wire, and we have the ground. The ground is just to complete the cycle. So that's why voltage will comes in if we have the ground. So if we have only one line, it is no longer a voltage. It is just a potential, electric potential. But if you connect the two, then it close the circuits, then we call that as voltage. That's why we are not allowed to touch the two wires in our house, our power supply. Why? Because if you touch the two, you are generating a closed circuit and it provides a voltage. But if you touch only one line of that, no, be careful that to wear no safety gears. You have to use shoes, no, in order to not to connect the ground because earth is a ground. So if you touch one line and you are touching also your feet touches the ground, then it has a closed circuit. That's why electricians or other technicians uses the hard shoes, no, steel shoes, steel two, or rubber. Why? In order not to ground. So again, to complete the circuit, we need the two terminals. Okay? So, meaning if you substitute the values of each terminal, the answer is still 12 volts. Now, sometimes 24 volts. Okay? So, this is it. This is how voltage generate using the two potential. So again, remember that the indirect charges provides the energy, and the energy per charge is electric potential. Now, if we have two potential, we can generate electricity. We can provide power supply. We can have a source of energy by using the two potential. So the two potential, subtract it, the result is voltage. So in order to provide voltage, we need 2 points. 1 point only of electric potential cannot provide voltage. It should be 2 voltage. And it should be, the ideal is positive and negative. So that when you take the difference, the voltage is greater compared to other. That's it. So therefore, okay, so thank you for listening. See you next